Welcome to Non-Euclidean Geometry Lesson 4. In this lesson, we'll define hyperbolic geometry. It's a matter of negating the parallel postulate and accepting the first four postulates of Euclid and the propositions that can be derived from Euclid's four postulates. The other point I want to make here is that this lesson it depends on lesson 3, which hopefully you have looked at, and future lessons will depend on this lesson and lesson 3. So you kind of need to go in order to make sense out of this. As I noted on the previous slide, hyperbolic geometry is based on the first four axioms of Euclid's geometry, the postulates we can prove from the first four axioms, plus the negation of the parallel postulate, i.e. the fifth postulate of Euclid. So we have many choices to negate the fifth postulate. As you recall from a previous lesson, we had several pages worth of equivalence. The one we're going to select is the equivalence statement listed here. Let me point to it. The summit angles of the Secchieri quadrilateral are right angles. Under the assumption of the fifth postulate, the summit angles are right angles. In other words, what I just stated up here. Hence, to assume that the summit angles are either obtuse or acute is to negate the fifth postulate. But we know from theorem 5, which we proved in the previous lesson, that the summit angles of the Secchieri quadrilateral are not obtuse. So if we only need to assume that the summit angles are acute in order to effectively negate the parallel postulate. That's what we've done here. So this statement is the foundation of hyperbolic geometry, along with the first four axioms of Euclid. The summit angles of the Secchieri quadrilateral are acute. And from this, we're able to prove quite a few theorems, which we'll see in this lesson and following lessons. I have an alternate drawing here of the Secchieri quadrilateral. The only difference from what I've drawn before is I've actually emphasized the bending here. And so the summit angles clearly are, from the figure, are acute. They're less than 90 degrees. And everything else is kind of as I've drawn it before. I've done this just to give you a sense of the bending that you have in hyperbolic geometry, but many of the diagrams, I'm just going to draw this straight, and you have to use your imagination that the angles here at C and D are actually acute. I will use this format a little bit more, but as I say, I'll get away from it later on, and I'll try to remind you when I do that. Okay, so let's continue. I have a few theorems to present here. When we negate the parallel postulate, as we've done for hyperbolic geometry, we also negate all the equivalent statements. And that actually gives us a lot of information. I've just listed a few here. Let's take a look at these. Given a line and a point not on a line, there exists more than one line through the point and parallel to the given line. Later on, we'll prove that given any line and a point not on it, there exist infinitely many lines through the point which are parallel to the given line. And these lines have a common perpendicular with the given line. There exist triangles whose angle sums are different. That's interesting. So this is a consequence of negating the parallel postulate. All similar triangles are congruent. That's also interesting. So we know from Euclidean geometry, you could have similar triangles with the same angles, but one could be, just a few centimeters, and one could be kilometers large, and they're still similar. But that's not the case for hyperbolic geometry. Similar triangles are congruent. They're exactly equal. The side lengths and their angles are the same. There does not exist any pair of straight lines that are a constant distance from each other. So this is sort of negating the parallel line concept from Euclidean geometry. There does not always exist a circle passing through three given non-collinear points. So 3 points don't necessarily determine a circle in hyperbolic geometry. These are all true statements in our new geometry that we're discussing here. Closely related to the Saccheri quadrilateral is the Lambert quadrilateral. The Lambert quadrilateral, also known as the Ibn al-Haytham Lambert quadrilateral, is a quadrilateral in which three of its angles are right angles. And I have a diagram of it below. The summit line is drawn, let me show it to you first. The summit line is drawn curved just to emphasize this is an acute angle in here, and then these three angles are right angles. A Lambert quadrilateral can be constructed from a Saccheri quadrilateral by joining the midpoints of the base and summit of the Saccheri quadrilateral. This line segment is perpendicular to both the base and the summit. So it might be easier to go in this direction here. If you take a Lambert quadrilateral and you copy it and then just flip it, you get a Saccheri quadrilateral. If you start with a Saccheri quadrilateral, this thing here that I'm tracing, and then you create find the midpoint of the summit and the base, draw the perpendicular. Remember we proved that the segment joining the midpoints of the base and the summit is perpendicular to both, and then we get two Lambert quadrilaterals if we do that, one on each side. So some of the theorems we'll see involve the Lambert quadrilateral and some will involve the Saccheri quadrilateral. Okay, and this is the relationship here. Theorem number 7. In a Saccheri quadrilateral, the summit, this here, is of length greater than its base, and the line segment joining the midpoints, this here, of the summit and its base is shorter than either arm. So this segment here is shorter than AD and it's shorter than BC. So we have two things to prove here. We're going to make use of theorem 6 from the previous lesson, which I just copied down here for our reference. So consider the Saccheri quadrilateral ADBC in the figure below, which I've already pointed to once, where M is the midpoint of AB and N is the midpoint of DC. And then we know from theorem 2 of the previous lesson that MN is perpendicular to DC and AB. So I've drawn that here. Now we can apply theorem 6. If you recall, theorem 6 you only needed to have right angles at the base. So we can apply it either to here and to this side both. So so first of all we say since ABCD is a Saccheri quadrilateral by assumption, then the angles D and C are acute. We proved that earlier. Then we apply theorem 6 to A, M, and D. And this angle here is bigger than that angle here. And from our theorem 6, we have that the greater summit angle lies opposite the greater arm. So this is the greater summit angle than the one at D. Again, we're just looking at this Lambert quadrilateral. So that means that this is AD is bigger than MN, or as I've written it here, MN is less than AD, same thing. Then we just we apply theorem 6 again, but to the MBCN. And again, the angle at N here is bigger than the angle at C, which we know is acute. So this side here, BC, is greater than MN. So we've proven basically the second part here. And the line segment joining the midpoints of the summit and base is shorter than either arm. So now we need to prove the first part. The summit is of length greater than the base. We need to show that DC is greater than AB. And we'll do that on the next slide. To complete the theorem, we apply Theorem 6 to Lambert equilateral AMND as before, except now we're going to look at MN is the base and AD is the summit of the Lambert quadrilateral, and then we'd have this leg here DN and this leg here AM. And since this angle here is bigger than this angle here, we have the DN, this segment here, is greater than AM. And then we do the same thing with this Lambert equilateral, but again we look at the base as being NM, the summit as being CB, and then these would be the arms NC and MB. And so we have that CN being opposite the larger angle here is greater than BM. Then we just add these two inequalities together and we get DN plus CN, which is the summit, is greater than AM plus BM, which is the base. And so the length of the summit is greater than the length of the base, which is what we wanted to prove. So that's the end of the theorem, but we have a comment here. Lines A, B, and C, D are parallel by Book 1, Proposition 28 of Euclid's Elements, since they have a common perpendicular, which is MN. Further, AD and MN are on equal distances, we just showed that, between lines AB and CD. Hence we have shown that parallel lines exist which are not equidistant from one another, which confirms one of the negations of the parallel postulate. So we have one last theorem for this lesson. I have a lot packed onto this slide. I wanted you to have the theorems that we use in proving this, so I kind of squeezed them in the bottom left, which I'll show you in a second. I don't have them displayed yet, but let's look at the theorem. The non-right angle in a Lambert quadrilateral is acute, and each side adjacent to the non-right angle is longer than the opposite side. So on the bottom right, we have a Lambert quadrilateral. Ignore the grayed out part. I'll get to that in a minute. So NMBC is our Lambert quadrilateral, and then the angle at N, at M, and at B, they're the right angles, and then the angle that's claimed to be acute is this one here, C. That's the non-right angle. We're going to prove that's acute. And then the theorem says that the adjacent sides here to the angle C are bigger than their opposite sides. So in other words, NC is longer than MB and CB is longer than NM. At least that's what's claimed here and what we need to prove. So in what we're going to do is extend this Lambert quadrilateral into the Secchieri quadrilateral, and let's do that. So the first thing is we extend the segment NC out to a point D such that DN is equal to the length NC, stated here. And then we drop a perpendicular down from D down to this line here, MB. We'll call that point A, and then this is 90 degrees. Okay, so let's look at these two triangles first, MND and MNC. So this line here, this segment is equal to that. Then we have a right angle in both cases, here and here. And then they share this side. So this triangle in here and this triangle here are congruent by side angle side, which means that this line segment dm is equal to mc, and then beta is equal to gamma. But since we have a 90-degree angle here and here, that means that beta from this is alpha, and that's the same as gamma from 90 degrees, which is delta. So alpha and delta are the same. And with that information, we have and I'll show you the theorems we're going to use here, the proposition 26 from Euclid's Elements gives us both angle side and angle side angle in terms of congruence theorems. What we need here is angle side. You notice we have an angle. These two angles are the same. This angle equals that angle, and then we have a side here that equals this side here. So by this proposition, the angle side aspect of it, we have that MDA is congruent to MCB. So this triangle here is congruent to this triangle here. And what that implies is that DA is equal to CB. But once we know that the arms are the same, and we have a right angle here and here, we know that ABCD is a Saccheri quadrilateral. And from the hyperbolic parallel postulate, we assume that the summit angles are acute. So we know that the D is acute, which we don't care about, but we know that C is acute, and that's what we wanted to prove here, that this angle C is acute. So that's half of what we needed to prove. The other half comes from theorem 6, which I've restated down here. If you remember, theorem 6 said if we just have a quadrilateral with two right angles, then we had a relationship between the sides, the arms. So first we'll look at this quadrilateral NMBC, where we have a right angle here and here, and this is the base and this is the summit. And then we have from theorem 6 that BC, being at the smaller angle here, is bigger than MN, this side here. Okay, so BC being opposite the larger summit angle in this quadrilateral is bigger than MN. And then you need to kind of turn your head 90 degrees clockwise and look at it, the same quadrilateral, but we want to look at this way here, so that NM is the base and CB is the summit, and these are the arms here and here. And then we have that NC is bigger than MB, and C is bigger than MB, because NC is opposite the larger angle here. This is 90 and this is acute. So we needed to apply theorem 6 twice to prove this second part of the theorem. Okay, so quite a bit to look at. I'll leave it up here for a few seconds in case you want to do a screen map or you want to just pause and have a look at it. But the theorem is up here. And again, we started with a Lambert quadrilateral. We extended it. We proved some things about these triangles. We proved this triangle is congruent to this. And then we used that to show this was congruent to this triangle. And then we were able to deduce that this arm was equal to that, which gave us that we had a Saccheri quadrilateral, which then gave us that C was acute. And once we knew that C was acute, we were able to apply theorem 6 twice to show the second part of the theorem, that BC was greater than MN, and then we kind of turned our heads 90 degrees clockwise, and we applied theorem 6 again and showed that NC was bigger than MB. Okay, so quite a bit there. Hopefully you got it, and we may need to use this later on, so keep this in mind.